So, as Pierre said, I'm Mathaios Panteli for those who have not been in my previous lectures. Currently, I'm an assistant professor at the University of Cyprus, and I also hold a position with Imperial College London, working closely with Professor Goran Strobak from there. So just a background, I mean, I did my degree in Greece, in the Aristotle University of Thessaloniki, up in the north. PhD at the University of Manchester, where I worked, as you see, for some years as a postdoctoral research associate, and then as a lecturer there, before moving back home in Cyprus in 2021, where I come from, as an assistant professor. So as Pierre said, we are now basically at the third seminar. So in the first two seminars, what we did, we started with, in the first seminar, looking at different ways of modeling different threats, different extreme events that can basically threaten the integrity and the resilience of power systems. So we talked about different quantification methods, different metrics, and so on that we can use. Then we moved to the second lecture, where basically we've seen how we can combine those quantification methods to planning models, and how we can build more resilient systems against extreme events. And so far, the impact quantification were more, if you like, static. So we're having the initial set of contingencies, we're running an OPF, an optimal power flow, we're quantifying the state of the system, that was it. In this work that will be presented today, we're actually going into more details to model the cascading propagation. So if you have an initial set of contingencies because of an extreme event in a power system, how those initial set of conditions can propagate across a system, which is what happens in reality. I will go through two models, and then I will discuss basically some applications we're doing in different projects as well. These are different projects that we worked over the years, which I went through in more detail the previous lecture, so I think I will skip this for the time being. It's just all the work that we're having in these 4 lectures is basically an accumulated work of many projects over the last 10 to 15 years. So here I just had an overview of all the projects, which, because most of you attended my previous 2 lectures as well, so I will skip them, so I will not bore you from the beginning of the slides. Okay, so the topic of the talk today. So cascading modeling is needed, just to set things straight and clear from the beginning, that there's a point for this work. Because as we said, basically you have the initial set of contingencies. For example, if a wind event trips down some lines, or if an earthquake destroys some substations, the impact will not stay there. It will propagate across the system with the activation of different protection mechanisms, usually automatic, that we have in place in order to protect basically the system. And this work, basically the seminar today will be talking explicitly about different cascading models that we developed. But before we go into the actual presentation, so what is a cascading? Cascading is basically, as we see here from the definition by NERC from the United States, is basically the uncontrolled successive loss of system elements triggered by an incident at any location. So as the definition says, and as we said, you lose some elements, and then you, in an uncontrollable way, you start losing more and more assets into your system until the cascading comes to a halt. There have been many cascading blackouts around the globe, which caused huge consequences on millions of people. So basically the 2 biggest from the last 20-25 years or so were from India. My Indian researcher complained about this. He told me there were more. That was like, this is the statistics, man. It's not me. It's the statistics, you know. So there have been many events that started from a single contingency and then propagated, affecting many people. So the causes can be many. It can be due to natural disasters, it can be due to human intervention, both intentional as well as unintentional. Intentional will have more these malicious attacks by cyber attacks now, and there is an increasing line of research now on how cyber attacks can actually trigger a cascading in power systems. And also some unexpected component failures, such as, for example, hidden failures of the protection or vegetation contact with the lines and so on. So all these things can actually trigger a cascading in power systems. When we have a cascading, when we have a disturbance, from observed data, we can basically have two phases. We can have the slow phase, and these are basically some data from one of the biggest blackouts that happened in the United States and in the world in 2003. So we can have the slow phase, where basically we have some elements tripping at a slower pace, which gives some time, let's say, to the operators to react, to apply some corrective actions to stop basically the cascading propagation. But after a point, basically the situation is irreversible. So you enter a state where whatever you do, the cascading will propagate. And it's what we see here in the fast phase, where you start losing more and more assets and elements in a very short period of time. So have the slow phase and the fast phase, which will come back in the next slides as well. So how we can bring this into one framework, let's say. It will have here in the middle the cascading events, also linking it a bit with what we've seen in the previous presentations. So starting from a resilient and stable state, you have your preconditional state. So you have your initiating system state, where you try to be robust, you try to be resistive, let's say, to the disturbance. Then you enter the cascading. This here we call it steady state progression, but it really refers to the slow progression of the cascading, where you have time to take some corrective actions. And then you enter the high-speed cascade, then you have your restoration. And then basically you have two ways of reacting to this. You have the short-term resilience, which you try to do something before, during, or after the event. And you have the long-term resilience, which is basically the investment planning that we discussed in the previous presentation. Hello, ULB people. Okay, so looking into statistics about the some of the cascadings that occurred recently, we have here some outages, some disturbances, and here we have what we call slow phase and fast phase. So this analysis was done from my PhD researcher in Manchester that Pierre examined as well, Matthias Noebels, who has very nice articles, by the way, if you want to read. So what Matthias did, he tried to see basically the slow phase, how long was the slow phase, how long was the fast phase across these events. So we noticed that basically the fast phase, okay, it's from some minutes from some seconds to minutes. And then the nice observation that we did from those data is that you start from 1 hour 40 minutes in the blackout in 1996, and then you drop down to 12 minutes. Now you can say this analysis is biased to show that we are reducing the duration of the slow phase, but indeed the slow phase is getting slower and slower, smaller and smaller. Pierre might not agree with this because we had that discussion. But because of the dynamics, because of the configuration of the system, everything now is becoming much faster. And that was evidence as well from the blackout in 2019 in London, where a lightning strike hit a line, and then in seconds, basically, they lost the demand. So there was nothing much that they could do there. So everything is becoming faster, and basically what we call dynamic simulations and dynamic cascading assessment is becoming more and more important, which we'll discuss today. What we also did with Matthias and Ian Dobson in this paper we have together in transactions, so we analyzed some data, some publicly available data from United States to actually understand the time difference between different cascading generations, different cascading stages. And we try to do that basically for all the events, and then we try to split those to small and large cascades, but also to events related to storms or not related to storms. And why we did this exercise? Because basically this helped us fine-tune a bit of the parameters that we're using in our cascading simulators in order to basically better understand the duration and the time between each outage you expect to get within your cascading. And then we try to basically map these times within the generations of cascadings that I will show later with Matthias' model. So the first model we developed with Matthias is what we call the AC cascading failure model, ACCFM, which is available in GitHub. I will show later the link as well. So basically this model is a recursive model. So once we see the disaggregation of the system into islands, some of the models stop there and they assume that the island will collapse, it will black out. But what we do actually, we go deep into each island and we continue running the cascading until basically the cascading stops within the island, or each further islands will be further formed. So we use AC power flow. We also, the nice thing with this simulator is that it can work and it can converge for a large set of initiating contingencies as well. So we go beyond the traditional n-1, n-2, but we do n-k. Where k, we tested our algorithm basically up to, I think, 10 assets failing as an initiating set of contingencies. And the model actually works quite sufficiently. The thing is, it's not a full dynamic, but we present basically the dynamics using static representation, using discrete time steps, which does not fully reflect the dynamic behavior of the system, which is a limitation of the model, but it is quite fast, and it can be used basically if time is of essence. You lose a bit from your computational accuracy, but you gain a lot from your computational time. So this is how it works. So we have frequency, we have voltage, we have load protection there, and there is a sequence of protection mechanisms that operate within the model, which basically are fine-tuned and aligned with what's happening in reality as well. As I mentioned, it's a recursive model. So as we see here, we determine the islands, and then we go deep into each island and run again the cascading until basically we get the stop at the end of the cascading within each island. So what you get when you run the model, which is, in my opinion, quite interesting. So you get this kind of tree-like representation of the cascading. So it's not as complex as it seems. So basically what this shows is the sequence of protection that operated during the cascading, and also by how much it operated, and basically how many islands were also created at each generation of the cascading. So starting from a healthy state, here on the top, this is just an example with a 39 bus system. We assume that you have the event, then you have overline protection operating, you have some under over-excitation limit operating as well, and then you see here that when you start losing some lines, the system splits into different islands. So for each of these islands, if it's healthy, if it survived, if it has enough generation, it's indicated by green. So basically those 12 nodes survived. Those nodes here, which are indicated by red, basically the nodes either because they didn't have enough generation or because the ramping of the generation was not sufficient to maintain the demand, they collapse basically. Here is the same, and the interesting thing is here. So you have these 20 nodes which were created here in the island, and then we carry on running the cascading within each island. So first you trip some demand because of under frequency problems, then this didn't solve the problem, you lose some more lines, you lose some more demand, and then you split down into more islands until you basically reach either a green or a red dot. And green dot means the node survived, a red dot means the node tripped. So this is basically, this gives a nice and quick representation of the cascading process because of an event. Of course, you can get many other outputs. You can get the reverse, let's say, of the trapezoid that we discussed earlier. So this is the loss demand as a function of the cascade generation, so the steps of the cascading process. So this is the loss load, Ines, not the energy that we discussed the previous time. And because it's a cascade, we don't model the restoration. So this is in megawatts, not megawatt hours. And you can also do many other things. You can increase the demand to see how the average loss load increases, or you can increase your flexibility in the system by adding more distributed generation in the system. And these bars basically show the percentage of lost load because of the operation of different protections in the system. And as I said, this code is also available in GitHub. If you go to download, this is also, I believe, quite well documented. It's easy to apply and to run and test yourselves. So we said earlier that dynamics are important, and it's what basically the limitation of the model we just discussed about, this ACCFM model, which represents the dynamics in a static way to increase basically the computational time. We also know that we have different controls that we can do. We have in different time scales. When we come to dynamic behavior, we have initial response, we have the primary control, we have AGC, the automatic generation control. Also, voltage regulation, power imbalancing, demand variation, and so on. And we also have different types of protection that we can apply for different, under different time scales. So events now are becoming faster and faster, as we said, because of this dynamic behavior and dynamic characteristics of the systems. So now we're talking more about the scale of seconds to minutes when it comes to cascadings. And because they develop very fast, so we need to get a better understanding of how the dynamic behavior of the system will be when exposed to an extreme event. So what we did, so the static models, especially the DC ones, as we said, they reliably converge, they're fast, and they kind of have an acceptable consistency with historical data. So what we did also, we tried to model the probability distribution of the faults we're getting with historical data to see if they match, and it's quite acceptable based on the available data in the literature. But as we said, we have the problems, especially in DC models, that we neglect voltage and reactive powers, and we also neglect dynamics. The AC power flow model, what we've seen with Mathaios, with the model by Mathaios, is a kind of addresses these issues, but not at the full perspective. So dynamics, as we said, are becoming increasingly important. So what we did afterwards with another student at the University of Manchester, which I still co-supervise, we developed another dynamic cascading simulator, which we tested in these two networks, which are publicly available, the 200 and 2000 Texas systems, which I will be showing basically the applications later on. So what this dynamic cascading failure simulator does, first of all, it's implemented in Power Factory. So we capture basically, for the time being, we only do frequency-related dynamics, but we're working now on voltage as well, as it's very important. We modeled the synchronous generator as a classical second-order model. I mean, the usual things we have in Power Factory. Then demand is a zip model, and it has also frequency response. And we model different sources, different sorts of protection as well within this dynamic simulator. So in order to make it quite automated, and in order to add quite, as we say, an automation in the generation of the events and the scenarios to actually simulate, we created an interface between MATLAB, Python, and Power Factory to run automatic a large number of scenarios. So this basically diagram shows a bit how the simulator works. So we have Python connected with Power Factory with API. We also have MATLAB, which generates the scenarios and generates all the visualizations after we get the events. And this basically are connecting a loop in order to automatically throw different scenarios to run in Power Factory and to run basically the cascading event in Power Factory. So this is how it works in a nutshell. So we first initialize the system state. Then we apply the initial contingencies using RMS simulations. We thought of doing EMT as well, but we stick to RMS at the end to try to get a good understanding of RMS first. Then we identify some network separation. If we have a network separation, basically we check if there is a generator there or not. If there is not, basically we deactivate the island and we update the network admittance matrix appropriately. Then if there's not an island, then we continue with solving differential algebraic equations of the new system. And then basically we check if there are new cascadings or not, and we repeat the same procedure to compute the final cascading metrics. And this is how it looks when it comes to which software does what. So we basically collect all the network information, we set up and adjust the parameters for the components, and we can also add controllers and protection relays. This is a nice feature that Etienne did at the University of Manchester. So she was my student, and when I left, she continued working with Robin Price there in Manchester, and we're still doing some very nice work together. So this simulator can actually add protection relays to any system. So it can automatically identify which relays you want the end user to add. It can basically build a dynamic version of a network. So this is quite smart what Etienne did, because what we were doing as supervisor, we're telling her, okay, apply to that system, apply to that system, apply to that system, and every time she was taking time to build a dynamic version. So at the end she said, okay, leave me alone for some time to build an automatic way of doing this. And then basically we take a system, we build a dynamic representation, and we run the simulator. Then basically we simulate the initial states in MATLAB, and we pass the results to Power Factory, and we create the initial set of contingencies, and then we run basically the simulation. We get the results, we process them, and we visualize them. We compare that model, which is the results that we'll be showing later, with NDC QSS quasi-steady-state cascading failure model. And the reason why we chose DC is exactly to see the limitations and to compare the limitations of using DC instead of AC. Just to make that comparison even stronger. And we have also results of comparison with the full AC cascading failure model. So this is quite simple. So we initialize the power flow, the initial state, then we apply the contingencies, we just do a check for network separation, and then we just trip lines, basically. Yes?
How do you determine the pilots? Is it random? Is it?
No, I mean, you might get, when you apply the initial contingencies, and when you have the first cascading steps, you might have some islands.
Okay.
Yes, this is what I mean. Is it clear?
Maybe it will be clear.
Sorry?
Maybe it will be clear later.
Okay. You can ask me later as well, if it's still not clear. Okay. So, okay, these are the comparison that we said before as well. So these are different, I mean, these are results that we got when applying the two models for dynamic cascades using the 200 bus system. So in the x-axis here we have the amount of answer demand, and here in the y-axis we have the probability of that answer demand exceeding a specific value. So we see the performance of the dynamic simulator, and we also see the performance of the static simulator. Now with the dynamic simulator, it's more likely to see small blackouts. And the reason of that is because, as we'll say later, there is in place this kind of protection mechanism, such as the under-frequency load shedding scheme, which basically sheds some demand at the early stages of the cascading, and it basically prevents the cascading from further propagating and creating bigger blackouts. And with the static and with the dynamic, basically we see, as we said, more smaller blackouts, and larger blackouts are less likely to happen. In the static model, you just strip lines, and you see the cascading, and basically there's not much of a protection to actually stop the cascading from further propagating. And you can also see different similar results when it comes to the number of line outages. So we have more, it's more likely to get, with the full dynamic model, a larger number of line stripping because of the dynamic model, and you have less probability of getting more lines tripping, again with the dynamic simulator. Now there are many reasons that we believe this difference happened. One is the model granularity, so the time step that we consider that we'll show later as well. So how granular is the model you're actually using, and if you have the data to actually build a proper model. The outages are quite lumped in the static, so there have been many models in the literature as well that we lump many line trippings into one step, so you can actually have a faster cascading before you can actually do something. And as we said, the under frequency load shedding scheme in the dynamic model, actually with small strips of demand, you can actually save the islands from going into total blackout. Okay? You're thinking about something, Freddy? No? It's also the data availability. You have the actual data to build a proper dynamic model, which a lot of the times we assume a lot of this data to build the dynamic representation, and also the computational burden. I mean, the dynamic simulator is quite heavy, and if we have to run it, if we have to run Power Factory for 100, 1,000, or whatever scenarios we have, it's quite heavy. It's taking quite a lot of time. It's actually one of the limitations we're facing in the HVDC-WISE project that I will talk about a bit later on as well. So with data availability, we said that basically we need the data to build a precise model, and also to have a precise event sequencing, which is quite important when it comes to actually simulating. If you want to simulate a realistic sequence that actually reflects reality, can be particularly challenging in these models. And also when it comes to comparing statistical information with simulations and tuning these models. Because we don't have a lot of data to actually learn from experiences, this is another challenge that we have, especially working with system operators. We run our simulators, and they're telling us this is not what we expect. I was like, I know, we know. So do you have the data to find your models? No. So this is what you are getting, basically. Yeah. Okay, I think I will skip this. Another thing that we also did in order to see the impact of the simulation step on the accuracy of the results, we varied basically the simulation step. So we started from 0.01 second, and we went up to 0.3 seconds to see the impact on the different metrics that we quantified from the simulations. And the reason we did this is because exactly it was very slow. So we started with 0.01 seconds to be as accurate as we could be. But then whenever we wanted to run something new, it was taking days to actually get new results. And by the time we're having another meeting with the student, we're forgetting what we discussed the last time. So we tried to see basically the impact of the simulation steps. So what we noticed basically, at least for our sort of simulations, if you see here from the expected demand not served, up to the step of 0.1 second, instead of using 0.01, the indicators were quite similar to some acceptable range. So we actually continue using this simulation step. Now, there are models, like the model of, how it's called? Eurostack, which using varying time step during the simulations, which is it's a very nice feature, but we didn't have that into our simulation. We're using a fixed simulation step. Now, what about renewables? So within the model then, we also added wind generation, and we actually added frequency containment as well with some batteries. And also we added the under voltage ride-through capability of the wind turbines to have some wind penetration within our simulators, and to see actually the impact on the initial response of the system. So we tested this on the 200 bus system, and we increased quite a lot the wind penetration, and we ran a lot of kind of deterministic and -2 contingencies. So these are some of the results that we got. So the indicator we have here is the expected demand not served with and without frequency support, frequency response, fast frequency response from batteries. And we also have the indicators, the metrics, condition of value at risk and value at risk at the 5% level. So we see here basically with black is the expected demand not served, with green is the VAR value, and with red is the conditional value. The dotted line is without the fast frequency response, and no, the other way around. With the dotted line with FFR, and the continuous line is without FFR. So what we notice basically here is that for the expected demand not served, as we increase, of course, as we increase the penetration level, the blackout risk and the unserved demand will be increasing because you lose from your system inertia, so it's easier to go into cascading when you have a big disturbance. Now, if we see the difference, how the two comparisons with and without the fast frequency response change as we increase the demand, we see that, okay, with FFR, the impact is less on expected demand not served, but actually the difference, someone would say, is not that big. When we go, however, to the extreme events, to the extreme disturbances, as those are quantified by these risk metrics, we see that as we increase the wind penetration, this difference basically becomes bigger and bigger. So the two, with and without the fast frequency response metrics, are actually diverging, and the difference is becoming bigger. What this means is that as the system is becoming more and more renewable-rich, as we need more and more fast response in the system, this kind of FFR strategies and actions that can actually inject energy quickly in the system are becoming more and more important when you have big disturbances in the presence of big renewables. And these are just some results about also increasing penetration level, quantifying the initial level, the frequency nadir, and basically we experimented on installing batteries close to the renewables or close to the demand, just to see which the comparison of these two and which actually perform better. Okay, these are just some results that show the reason of the load shedding. We actually, Etienne clearly split the reason into three main categories. So one is the intentional load shedding. So intentional meaning from the protection in order to try to save the system. Inflexible generation, what basically means that the generation that was in the island couldn't react fast enough to save the system because of slow ramp rates. And also zero generation, when basically the island has no generation. And we did this again for increasing penetration of renewables. And this is the split basically that we're getting for the load shedding and the rich wind penetration. Now, the other interesting thing that we did and that we discussed with Pierre also this week is basically we try to run the model for different demand levels. In the literature, what most people did, they focus mainly on this area here, where we basically have increasing demand levels, and as the demand, of course, increases, the blackout risk increases, which is quite expected. So what we did, basically, we tried to run it from low demands up to very high demands for both the static model and the dynamic model for different generation margins, basically reserves in the system. So we noticed basically this bump here in the low demand region, where basically instead of having this kind of trend, a quite low blackout risk, we actually had this higher risk around the region of 50 to 60 to 70% of the demand in the system. Now, why this happens is because basically when we're having lots of renewables penetrate the system into a single point of the system, for example, we have a lot of offshore connected at a small number of points in the system, part of the network will be overutilized. So if you get a disturbance, if you get an outage to that overutilized part of the system, then it's very easy for that disturbance to propagate across the system, even in periods of low demand. Because periods of low demand actually happen during night, and during night is where you have high wind, usually. So the combination of high wind and low demand actually can lead to higher blackout risk. And we actually kind of confirmed this finding with a couple of system operators in Europe. And they are actually confirmed that with the increasing offshore wind penetrating the system or areas of concentrated high wind areas, this is getting an increasing concern for the safety of the European systems as well. So another work we did in this, with this model is basically identifying critical lines for the network of security. So critical lines in the sense basically of how much they are actually contributing to the resulting load shedding. So know if they triggered the cascading or how many times they actually appeared in a cascading, but how much demand they actually resulted in being not served. So you can basically identify different lines here, and also what we did for each of these lines, we tried to hard constrain them to a lower limit, to 60 to 70%, and then to basically try to redistribute that power, to transfer that power to other lines as initiating contingencies to actually see how the blackout risk changes. And indeed, when we actually when we constrain more and more those lines, which comes at a cost, of course, because if those lines were rated, let's say, loaded to 70 to 80%, it was because of economic reasons of the more economic dispatch. But we actually try to retransfer, to redispatch that power through other routes. It will be at a higher cost, but the cascading risk will decrease. And this model is also available in GitHub. If you want to download it again and have a look at the model. Okay, so moving on to the HVDC-WISE project, which is a very nice project led by Supergrid in France, from Paris, not Paris, Lyon, yes. So it's a very nice consortium with system operators, consultants, universities, and so on. So what we're trying to see and understand is to address basically most of the challenges that we discussed over these 2 and 3 lectures now. So we have an increasing rate of equipment failures, we have this kind of extreme events, we have technological changes that are actually testing our system, we have different malicious attacks and so on and so forth. So we're trying to basically test different HVDC technologies and see how those technologies can actually act as a firewall to the propagation of a cascading within the same area or within connected areas with HVDC links. So in this project, our role, we are not HVDC experts, just to clarify that, okay? If there are any questions on HVDC, I will try to answer. Just to put that straight out, okay? Because I know the colleagues from Leuven will ask you about HVDC. So our role in the project is to basically bring together what we have available as technologies in Cyprus. So we have the fragility-based event simulator, which is the resilient tool that we discussed in the last 2 lectures, which basically can simulate in a spatial and temporal way a weather event as it moves across the system and how that damages the infrastructure. So this is this part here. And then basically the user. So now we are in the process of building an interactive user interface. The user can actually choose to implement either the static, the AC cascading fault model that we see, which is quite fast, or to choose to run the full dynamic model. So as I said, the AC cascading failure model that we have is fast and does not fully model the dynamics, but it does a good job. The full dynamic cascading fault model is slower, but it gives you a more realistic picture of the system performance. Then we have the cascading, propagation, and quantification. And then what we are trying to do now is actually implement some operational strategies, such as, for example, different islanding algorithms to see how we could potentially stop the cascading from propagating. So all this has been developed in a modular way. So basically, there is the main module, of course. There are the different sub-modules that you can choose to use or not use. And we're using, as we said before, for the dynamic cascade simulator, Python, MATLAB, and Power Factory. So for cascade quantification metrics, what we are using for the time being is the expected demand not served and conditional value at risk. And of course, we're focusing on this first area of the resilience trapezoid when we're modeling the cascading propagation. And these are just some examples. This is just an example of simulation with the 39 bus system. So we use this kind of simple model that is being used in quite a lot in the literature. So we have the 39 bus system connected with the 14 bus system with an AC link and also with a point-to-point HVDC link. We model here some controls and protection relays, as we discussed, and we have different initiating events from expected events n-1 going up to n-3 and n-5 or 6 in order to model this kind of tail risk events that we have in terms of big disturbances. Now, what the simulator can do, as we discussed, and this is just an example where we have a combination of lines, a combination of two lines of outage in the 13 bus system. So what we have here is a comparison basically of connecting the two systems with an AC line, and we see basically the resulting demand not served in the whole system, and also in the 39 bus system and the 14 bus system. And when it's actually connected with a DC link here instead of an AC link, so we have an AC and DC system, we managed to get a 21% improvement in the load shedding. So to some extent, the cascading propagation from the 39 bus system to the 14 bus system was actually mitigated. We're trying now to test different technologies of HVDC was provided by different partners in the consortium to actually try to understand why this is happening. So what control measures are in place, and then how we can actually control the HVDC links to act as a stopping, let's say, measure against the two, and against, let's say, the cascade propagation from one area to another. And then you can also get this usual, representation of different measures, and you can pinpoint exactly what happened in your cascading simulator, which line tripped, which basically under frequency and where under frequency load shedding scheme was applied, in order to compare the two with and without the HVDC link. Here, where the 14 bus system basically experienced a frequency problem is where the HVDC link was isolated. Not tripped, it was isolated because of different trippings of lines around the HVDC link. So this frequency basically problem here was when the connection between the two systems was actually lost because of trippings in the neighboring lines of the HVDC link. So what we did also afterwards, after testing a few scenarios and checking those scenarios with our dear colleagues in the consortium to make sure that they make sense, we started running different number of contingencies under n-1, n-2, and n-3 criterion. So this is 53 random contingencies of lines, so under n-1. Comparing here is the AC probability distribution, AC link, with a DC link in grid-forming basically mode. So what we have here is basically we have this kind of big number of tail risk events, so high impact, low probability events, so we have a high demand not being served. which we don't have when we have the HVDC link. So in a way, we curtailed, not we, the heavy tail events were actually moved more to the left, which means we're having lower load shedding in the presence of the DC link. And this performance was also observed for the N-2 scenarios. So we see here that we have a larger number of these kind of big events compared to the right picture where we have the HVDC link. But when it came to big contingencies, to three conditions at the same time, what we noticed, indeed, the tail was improved, but we also had a much higher frequency of lower impact events. So here basically it comes the dilemma, if this is preferable or acceptable or not. So here on the one hand, you reduce the impact of the big events, of the extreme events on both systems, but on the other hand, you actually increase the frequency of the lower impact events. And this is something we're still investigating. Why is this happening? And as I said, we're trying to test basically different technologies to see how they behave under different sort of disturbances. In the project, we'll have three use cases. So we have the mainland European system, which will use a simplified version. We have the Great Britain use case, and we also have a case where we're looking at the offshore systems of UK connected to the European system. And here we have basically the different resilience events that we consider within the project, which are directly provided from the system operators in these areas. And that will be mostly involved in case 2 in Great Britain, also providing the models for implementation for the other 2 use cases. But I will be involved, hopefully, only in 1 use case, hopefully. Although I know it will not happen. Okay, so Pierre, I think I will be finishing in 10 minutes. It's okay?
Perfect, sir.
Yeah? I will try, at least. Okay, so with the models that we've shown now, today, you can actually do a lot of things that we did within our work. So you can do what we call cascading aware control islanding. So islanding basically refers to the strategy that you try to split the system into self-sustainable islands, either before the event, during the operational planning phase, so which refers basically to the preventive islanding, or during the event, where we have here the cascading propagation, which refers to the corrective islanding. The preventive islanding, because in order to split the system to some islands, you may need to curtail some demand. And the definition we are using for this curtailment, if it's preventive, is controlling demand, not curtailing demand, controlling the demand before the actual event. So we built basically a full framework which helps you. This work is currently under review. So you can choose if you want to use basically the short-term operational planning option. So if you know that the event is coming, you can basically choose to do this in a preventive way, which is a bit more deterministic, or you can choose to do it in a more stochastic, in a more corrective way, in near real-time operation, when you have an ongoing event. And we have here basically 3 actions, basically 2. So we detect the splitting, if there is splitting because of the initiating event. Then we run again the cascading fault models. Here we're using the AC cascading fault model just for the sake of computational time. And then we actually try to see if there is a cascading. If there is not a cascading, there is no point of splitting the system, of course. If there is a cascading event, but still the demand is not, the impact is not that high, we just reduce the load to save the system. And if there is a cascading, what we do, we basically apply the tensional control islanding, where we identify the coherent generators between them. We create basically some coherent groups of generators, and we do the controlled network splitting. And here are just some results, which I don't want to tire you further with this. So the X's here are the initiating events. Then we have the cascading faults in the system. Again, this kind of tree-like graph of the cascading. And then when you actually control, split the system into islands, you still have a separation of the system to islands. You still have some load shedding, but that is reduces significantly when you actually effectively island your system. What we also did cascading aware or cascading constrained, let's say zonal black star restoration. So if you reach a system where you are in completely black star, so you lost all your demand, how you come back to energizing the system following such a big disturbance. Now, what we did in this work, there have been some zonal restoration models, of course. So what we experienced, what we noticed in real experience when it comes to black star restoration is that when the system operator tries to implement an action, and if you see the data from big blackouts, the demand goes up and then goes down, up and down, because they are trying basically to energize some assets of the system, which might lead to further cascading, to further instability, and further tripping again of the demand. So what we try to do here, in simple words, is before the implementation of every restoration action, what we do, we run the cascading fault model. So we assume that that line will be energized, or that generator will be brought in service, or that demand will be restored. And before we actually do that, we run the cascading fault model, and we see if that will lead to an instability. If it will lead to an instability, we basically constrain the amount of demand that you can restore at that simulation step. And then we do that repeatedly until we actually restore the whole system. And at the end, this is how it looks like. So we have the initiating event with the cascading simulation here, and then we have this step restoration of the system. And you see this kind of steps here because we assume this kind of 5 minutes restoration window for each of the simulation steps. I think I will pass this or not. Okay, so what we're currently doing in the R22 project, which you can see in details from the beginning of the presentation. So we have a cascading. So the idea is to identify, as we said earlier, the critical components when it comes to their contribution to the cascading propagation. So what we did, we developed different machine learning models, machine learning approach, to actually simulate thousands of cascading models, train, of course, these kind of machine learning models in order to identify the classifiers and then to basically identify the critical components of the system for cascading analysis. So what we did, we tested 5 different models, which I do not remember all of them now. It's in a paper. So we tried to basically compare how many of those algorithms agree for the identification of the criticality of the lines. So here we have the number of algorithms agreeing for the criticality of a line, and here we have the different components that we identified as critical, focusing only on lines in this occasion. So we can see that for this kind of first, I think, 12, 13 lines, all the algorithms agree that basically these are indeed the most criticals, and then we'll start having some disagreement when it comes to the different algorithms on ranking the criticality of each of these lines. And we also did the sharp value analysis here as well, which agrees with this analysis here when it comes to the identification of the most critical components in the system. What we also try to do, and what we are doing now, is to try to predict in a fast way, the load shedding that you can get from a cascading. So if we have this actual load shedding and we actually have the predicted, we try to match the two. We try to basically be as accurate and as fast as possible in our prediction in order to assist system operators to make a fast decision either before the event or during the cascading. So what we did in this work, which is currently under review for the CEST conference, we generate all sorts of contingencies, n minus 10 minus 3, as well as stochastic contingencies with the wind simulator we have. We quantify the nodal load shedding using a cascading fault model. So we generate then the data set of the contingencies, and then we compare different individual models with a stacked regressor model. So with a stacked machine learning model, which is much more efficient when it comes to accuracy and efficiency. And then we evaluate basically each of the models using the R-squared metric. And these are just some results you are getting for the 39 bus system and the 24 bus system when it comes to the R-squared metric of each of the bus we have here, where basically we see that the stack model overperforms all the other individual models. Now, the interesting thing that we noticed in this comparison, we know that the 39 bus system is quite robust, it's quite reliable. No, it's not, sorry, it's not reliable, the 39 bus system. Yeah. So basically when we trip a line or when we trip two lines, we get load shedding, so we can train our simulate, our models, everything is fine. With a 24 bus system, which is more reliable, for n-1 or n-2 contingencies, our data set basically was of big load shedding cases were less. So the model was not able to be properly trained. So that's why we're also getting some negative R-squared values here, where basically it's better if you don't predict and you use an average value rather than using a prediction from these machine learning models. So what we've shown, what we believe we've shown with this work is that basically the more reliable the system is, I mean, it's quite expected as well, the more simulations you need and the more you need to stress the system in order to create this kind of cascadings and the load shedding cases to train your models to achieve high accuracy. Yeah, and the last thing, the very last thing, is we try to do what we call the cascading-driven investment planning. And this work will be presented in PSCC in June in Paris. So I will not go into much details to keep something for surprise in the conference. So what we did here, basically, we tried to merge the two, the investment planning work that we presented in the last lecture with the cascading models that we have in this work. And this is important because usually the cascading impact is not considered when you're trying to quantify the impact of an event, which then goes into the cost-benefit analysis for an investment. So by ignoring the cascading, you ignore a big, basically part of the impact of a specific disturbance. So what we do, we try to integrate basically the cascading impact into the investment planning. And we actually show that for the same budget with a bit of different options, when you are actually considering the cascading, lots of the metrics that we used, including the demand not served or the number of active, passive islands, and so on that were formed during the cascading is actually very much improved when you consider the cascading. And my researcher had another idea. So in order of using a fixed alpha, so a fixed, let's say, threshold for the conditional value at risk and the value at risk quantification when it comes to the extreme events, to basically try to develop a machine learning algorithm to learn from the frequency and the impact of different events to make sure that you don't miss any big events. Because if you set the threshold at 5%, at 5.001, there might be another big event that you're missing. So the point of my researcher was, why do we use fixed values? My response was, because that's a decision from the system user to define. And by my researcher said, why don't we try to define basically that alpha? And this is what we try to do here. So we try basically to define your risk-averse approach, if you like, by defining the range of the extremes to consider, how that affects your investment decision making. And that was it from me. Thank you, Pierre. I will be very happy to answer any questions as best as I can.
Thank you very much.
Thank you, guys.